functions exist. Okay. I will show the documentation and tutorials at the end in order to bait you a bit into watching the rest of the video. Okay, so now we will delve headfirst into the Lie group formulation because it's in Pinocchio, and because again, if you're gonna spend some more time with robotics, it is worth learning. According to me and some other people. Okay, so what is a Lie group? Okay, so I will bring you to why we even need this this concept first. So you know your frames, you know how to transform between the frames. Basically, that means is you know what homogeneous transformations are. If you know this, you're good to go for using the library. But you need to know this to run anything on the robot anyway. You don't even need to go much beyond that if you have a URDF. But now we have a problem. Okay, you have, and this is where the Lie groups will come in as the solution. So if you have one rotation matrix or one homogeneous transformation that contains a rotation matrix within it, and you have a different one, and you want to plus them together to sort of have the overall transformation, let's say, you wouldn't get what you want. You can't plus them together. That's because they do not form a vector space. So there's no pluses and minuses. There's not even directly a scaling, multiplying with a scalar number that works. Okay. And because of this, so this is for rotation specifically, this does exist for translations. And now people have in robotics like a million different solutions. And by million, I mean like 6 different representations of orientations and so on. They all have something that's good or bad about them. The Euler angles are the worst. Please don't use that. That's all I will say on the other representations. But what I'm getting at is the fact that these homogeneous transformation matrices don't form a vector space does not mean that we can't do things with them, that we can't compare them, that we don't have the option of composing them and so on. It's just that in order to do this, you will need to learn some more math, and that will be the Lie group math. So let's pretend we don't know anything about coordinate transformations, things like this, and build this up from scratch again. So the first concept that we need is the concept of a mathematical group, and I will read the definition for you here. A group is a non-empty set G. So set G, that could be a real line, it could be 5 different numbers, whatever. Okay, some non-empty set G, together with a binary operation on G, denoted by the dot. This is the central dot. Okay, so we have some binary operation, so this means it takes 2 numbers as inputs, or rather 2 elements of the set G. That combines any 2 elements A and B of G, so they're elements of G, to form another element of G. Okay, so the output is something that also has to be in G. We denote this operation by A, C dot, or times B. But this does not have to be multiplication, okay? It's just any binary operation that we just denote by this dot. And this operation has to satisfy the following 3 requirements, or the group axioms. Okay, so we have associativity. So while the order does matter like this, whether you compute this first or this first doesn't matter. There is an identity element. So if we left or right multiply with the identity element, what we started with doesn't change. And finally, there has to be an inverse element, which means that if you multiply the one element with its inverse, you would get the identity element. And the same thing has to function in reverse. Notice there's no commutativity. That's why we had to write this out 2 times. Now I will immediately I want to give you the examples of these Okay, so that was a group. A Lie group is a particular kind of group. Okay, it has a bit more properties. But I want to give you an example first. So if you have the general linear group, that's all matrices that have an inverse defined. So they have to be square matrices, and they need to have well-defined inverse. So they have to be full rank. Then you have the inverse element, because you can do the inverse of the matrix. The identity element would be the identity matrix, and the operation would be matrix multiplication. All right, so I wanted to say that first. Right. The second concept we need, well, we don't really need, I just want to say sort of where this all of this sort of comes from. It comes from differential geometry, which is studying geometry and curved spaces. Now, you won't need the concept of a manifold for anything here. And instead, I'll just give an example and say you can abstract this away. The example is the Earth, the globe. So we live on the globe. And when we're traveling around the Earth, we don't really care about we only care about 2 dimensions. So you can go along the geographical width and the length. Okay, there's no one's gonna travel into the center of the Earth. And okay, we do have space explorations and flights and stuff like this. So sometimes we go a bit up, but if we consider the Earth to be a pure sphere, it's two-dimensional. It's a two-dimensional object embedded in 3 dimensions. And then if you want to say something about what's happening on the surface of the Earth, ideally you want to use the 2 numbers for the 2 dimensions that you have. But since the Earth isn't flat, like Euclidean space, you also can't just take this point, plus them, and get something meaningful, right? Because you want to embed the fact that this is curved within your geometry, within the things that you do and the math you define on this. Okay, so this is the second thing we have to consider. Now let's talk about Lie groups specifically. So the underlying the set G is now a smooth manifold. That's something like the sphere. Okay, just the outline, just a 2-dimensional outline, and any sort of smooth surface would be a manifold as well. There's a technical definition for this, and for everything that I'm bringing up, I'm just gonna skip over all of this so that you just have a feeling for what's going on, and I will refer you to books and resources in case you do want to learn more about this stuff. And anyway, now our group operation is some function that has to be smooth, and this encapsulates the group axioms by itself. This should be a minus to the power of -1, or the inverse. Okay, so if we have, as mentioned, we mentioned a group. Now it turns out that matrix multiplication on square invertible matrices is in fact a Lie group, not just a group. The Lie group have some additional properties. Okay, now we get to the stuff that we actually want. So the orthogonal group is the group of matrices that's a subset of the general linear group, where if you have this matrix times the transpose, you would get, they all have determinant 1. Determinant 1, that's how they're defined. Or rather, determinant 1 or -1. The special orthogonal group is when the determinant has to be +1. And you can show just on the basis of this that then 2 matrices that are within the special orthogonal group, that matrix A, let's say, times A transpose would give you the identity matrix. And then from this you can derive further properties that I won't do, but okay. If you have the special orthogonal group where this M is free, so it's 3-dimensional, that's a rotational matrix. This is why we care about this stuff. And now we're going to use so it's not a vector space, but we'll use this group property to show what we can do in this space. Very importantly, this is in red. These groups, I'm talking as the example about the matrices, but in the abstract sense, these groups do not have to actually be matrices. That's because they, if you have a 3x3 matrix, there's 9 numbers inside of that, which would make it 9-dimensional. But if you have these restrictions that the determinant has to be +1, then in fact, this group will be 3-dimensional, which means that some of these numbers don't mean anything. Well, don't mean anything. They depend on the 6 numbers depend on the other 3 numbers. Now, we embed these 3 numbers, we add the other 6 to make it an actual matrix, because then we can do these operations, like the group operation can now have a particular meaning that we can use. Okay, so some of the things sometimes you want to define and calculate and prove in the abstract, where you don't care about the representation. And in fact, I mean, we could conjure up different representations for the SO group. It doesn't have to be a rotational matrix. It could be something else. For example, a quaternion. So you could use quaternions to represent elements of the special orthogonal group, the unit quaternions. And the key thing is, once we know about groups and their underlying structure, we don't care about the particular representation anymore. The particular representation is simply whatever we have out there in math that would fit, that would comply with the abstract definitions. Okay, it's very, very, very important. That's why it makes sense to learn this stuff, because then you don't have to care about the particulars of the representation, and then the things just are a bit more clear. Okay, and then we have the Lie algebra, and I will introduce this via this picture. Okay, so this circle that we have in the background, that would be a 2-dimensional sphere that's embedded in 3D space. And now, let's say we have some sort of a line that goes over this circle. Okay, we're on the Earth and we're traveling somewhere. We need to have, if we say, okay, I have a parameter t that describes this curve. So this curve is some function of t, and I'm traveling around. What happens if I take the derivative with respect to t, which would be time, of course, for our practical purposes. But what would happen? So normally in Cartesian space, you would write the arrow, and you would say that this is now your tangent velocity. If you remember from physics class, if you were something was you had some rotational motion, you're circling around with something. Let's take this earphone. You're circling around with something. Then at every point, the tangent vector would be pointing outward. And it would change all the time. So this thing would remain, its trajectory would be a circle. Now, for mathematical reasons, this is actually defined slightly differently. So I would say, it's quite a journey up until you get and understand what the more abstract definition of a tangent vector is. It's a differential operator that satisfies some properties, whatever. For our purposes now, it might as well be an arrow. Okay. The reason why we don't want arrows normally is because if we say, okay, we want to define everything on this curved space, then we don't want elements sticking out into what's called the ambient space. We want everything to make sense just in the curved space. Okay. If your underlying manifold, so this circle, this sphere, is a Lie group, then I should have said. So if you have this tangent vector, and you could have a different curve going around here, passing through the same point, then you would have different velocities at the same point. Of course, if I'm here, I can move in any which direction. Anyway, these velocities do live on a tangent space, so you can plus them together. You can multiply them with a scalar, do your normal linear algebra with the velocities. And furthermore, if your underlying manifold is a Lie group, then this vector space would be called a Lie algebra, and it has some additional nice properties, which we don't need for this very short introduction, giving you a flavor for what we have here. But there is something, so I wanted to explain that log6 function in Pinocchio. So if you have this tangent vector and you apply an exponential map on it, you will find the operation, the group element, that if you're at y and you multiply it with the exponential of this vector, of this tangent vector, then you would end up at this point. So basically we have a correspondence for getting from one place to a different place, right? But we didn't plus these two elements together. Instead, we had the tangent vector that takes us there. We used the exponential map to define the rigid body transformation. I'm constraining myself to the fact that we want to use this for rotations in 3D Cartesian space. Then we would get to this point. Okay, so it's a bit more involved than just plussing, but you can do the exact same thing by leveraging the fact that this is a group structure and that we know some additional things about it. Like, for example, we can, if you go into the mathematical depths here, you would be able to say that on Lie groups this exponential map is always defined, which is not true in general, and so on and so forth. And if you have a group operation, so one element times the other element, that gets you here. If you take the exponential map of that one of these elements, then you would find the tangent vector that would be, that if you exponentiated it would correspond to this transformation. Okay, and for our purposes the logarithmic map will be well defined. Okay, and now let's just go all out with the primary group we care about. That's the SE3 Lie group. And it has, if you write it in small letters, SE3, that would be the Lie algebra. Okay, so if you combine the 3 dimensions of position plus 3 dimensions of orientation, so you combine an element of R3, so 3-dimensional normal vector space, and you stick to it an element of the SO group, so a rotation matrix if we're in 3 dimensions, then we would have this element. And for us, that's the pose of the robot. Okay, so that's I'm not changing the position, but I am changing the orientation of my end effector, my hand. And we'll call this the pose. And this is a 6D thing, although we would represent it as a homogeneous transformation matrix, typically, because that's the easiest thing to use. And that has way more numbers. Okay, so even though it's 6-dimensional, we add these different numbers so that we can have a group operation of matrix multiplication and then have all of that satisfies all of these properties. But like I said, if you instead choose to represent this with quaternions, then the SE3 group would look like something else. It wouldn't be a homogeneous transformation matrix. And the point is, again, that's what I'm driving at, is that these representations don't matter if you understand the Lie groups in the abstract. Okay. Now, what would be a tangent vector of the SE3 group? That would be, the small SE3. We call this a twist, and since this twist does live in a vector space, that can simply be a 6D vector. Okay, and the same would go for the combination. So the tangent vector velocity here, so it's the 3 linear velocities and the 3 rotational velocities. And the same would go for the combination of force and torque, and we call this a wrench. And you're in some particular coordinate space, you want to map a wrench to some other coordinate frame, not coordinate space. And there's a bunch of operations that are defined for all this. And if you want to understand all of this really well, I'm sorry, but the only way to really go for it is to read a book. Okay, there's a bunch of details, a whole bunch of details that I skipped over here, that are essential to using this correctly and effectively. Now, thankfully, since all of this is visual, we're not doing the actual Riemannian geometry in the abstract and dimensions. You can visualize all of this, okay? So you can help yourself learn until you understand. You play around in a shell or something, you plot all of this, and it will work in the end. But I do want to simply enumerate some of the typical things that you would want to know. So the properties of orientations. This is from an excerpt from a book. I will show you what the book is. This is when you connect this through linear motion, form rigid body motion, so SE3 group. Here is how you would define, how you would get from a free vector to its SO3 representation. That would be a skew-symmetric matrix, and so on. The math behind this is relatively straightforward, and it's very, I would say it's very fun and informative to prove a lot of these different identities. And anyway, here we have some transformations that we would typically do with rigid body motions. Okay, so this, if you understand everything that happens on this page, you have all of this defined in Pinocchio, and you're good to go. And you don't need to know the depths, the mathematical depths. Okay, I just added them here so that they're less scary in case you do want to go for that. If you go through this particular book by page 115, you will know everything there is to know. It's a worthwhile investment if you plan to work in robotics in the future. Okay, and now finally let's enumerate the different resources you would use to know all of this in depth. Okay, so number one would be Pinocchio documentation, and I will open it up for you. There we go. Do I have? Okay, does this still work? Yes. Okay. And let me put my face back on in the corner. All right. So this is the all of these links will be provided in the GitLab. That will be in the description once all the tutorials are done. Anyway, here you have all the information about Pinocchio with more words explaining and going over everything. And if you want to see if it's open source, of course, and if you want to see the details of every different class, there is a reference for all the classes here. Now this documentation is a bit imperfect. Okay, now we left the realm of the Python packages that everyone uses, where the documentation is phenomenal, like the standard library for Python or scikit-learn. Now we're depending on projects that are maintained by a single-digit number of people, and they want to develop more features rather than go through and have perfect documentation. But having this said, there are tutorials, apart from the documentation itself. Now they do assume that you already know enough of the robotics to understand what's in the tutorials. So you do have to have some sort of prerequisite knowledge to go over it, but you can do this in tandem with your robotics learning from the books I will list further below. Let's open up a tutorial just to show where they are. Oh, come on, open the link. There we go. No. So in this particular GitHub repository, you will find probably the best overall introduction to Pinocchio. Wanted to bring it up. To show it's there. You have very nice Jupyter notebooks if you want to go over this. Now, Pinocchio also has Casadi support. So if you want to do optimal control, then I would recommend this particular tutorial that goes over this in depth. Now, the version of Pinocchio used in this tutorial is hard to install, but they do provide a Docker image, so just run this Docker image. That's what you want if you want to use Pinocchio with Casadi. Of course, you could compile the new version of Pinocchio with it, but for teaching purposes, just run this to get the notebooks that explain everything very well, very well. And there are also some exercises that are offered on the official documentation. Not all of them have solutions, but if you're able to read these questions and answer them yourself, you know everything there is possibly to know with Pinocchio, essentially. You're good to go, and you know your robotics as well. So this is this would be, if you know this, you can do what serious stuff in robotics. Okay, so those would be the Pinocchio tutorials. Now let's get over into some books. So the chapter summary I showed you is in this book, Modern Robotics: Mechanics, Planning and Control by Kevin Lynch and Frank C. Park. This is the book to learn all of the sort of the more mathematically things in the introductory sense. So it goes over what the things you need as quickly as possible, and they also have a lecture series on YouTube. So if you type in Modern Robotics Kevin Lynch on YouTube, you will find the lecture series for the whole book. That's of course not just these transformations, but robotic control, some things in modeling and so on. Amazing resource, and they have the video supplement website as well. Okay. So this is the introductory book if you want to go down this route for this type of mathematical representation in robotics. If you want the OG version, then this is the book, Mathematical Introduction to Robot Manipulation, Richard Murray, Lee and Sastry. I'm sorry, I won't attempt to pronounce their names because I know I can't. This book is very good if you want to do dexterity, because it goes over hand dynamics, the contacts, and stuff like this. Okay. Now, if you saw this short tutorial on Lie groups and you said, "Oh my God, I never ever want to think about this ever," then this is the book for you. Robotics, Modeling, Planning and Control by Bruno Siciliano and co-authors. This is the book with which I learned robotics. It's even if you said I want to only use Lie groups for the end of time, I don't want to be bothered by anything else. This is a book that's still more than worth reading because it has a lot of the control is a bit more serious here, and some people in robotics don't use Lie groups. They prefer to do it by separating. They prefer to do it the other way, and this is the book you would want to go for that, so that you can read any paper on robotics that you want. Yes, okay. And finally, since I'm showing off books already, the Handbook of Robotics is the book to get started with the robotics in the wider sense. So I know this is in the Pinocchio library tutorial, but this is a thick book. If you want to, the second half on the application says bit so and so, but the first half every single topic in robotics is enumerated, and it provides the key papers in this subfield. So great book to peruse. This is all that I used, and if you went through these two books, you will. I should have noted as well, for Pinocchio you also need another book that's Roy Featherstone, Rigid Body Algorithms. I don't know why I don't have it in a tab here. That's again Roy Featherstone, Rigid Body Algorithms. I think I did have his website prepared already. No? Okay, I am here. Roy Featherstone. In his homepage, you have some information on this, and the book is available here. Okay, this is the algorithms described in that book is what is implemented in Pinocchio. If you're doing some dynamics and things, you definitely, that's it. That's the peak. It's incredibly efficient, and you will know exactly what's going on in the code. Now, finally, there's a series of lectures on Lie groups and Lie algebras. If you want to have the mathematical underpinning, if you're a more mathematical person, go look at that. Jonathan Evans, very nice lecture series on this particularly. And he doesn't go into the smooth manifold stuff. So, there is a place for that in robotics, but that's very advanced, and I don't think that you should start off with that. And finally, Kevin Lynch with video tutorials, so that you can, it's easier to know what you're reading if you watch the video on it first. That would be it for this tutorial. Thank you for your attention.